Well, welcome everybody to today's Physics and Astronomy Colloquium. It's a great honor for me to welcome Professor Subir Sachdev, who is the Herschel Smith Professor of Physics at Harvard University, specializing in condensed matter physics. Professor Sachdev has made many pioneering contributions to many areas of theoretical condensed matter physics. He's played a key role in the development of the theory of quantum critical phenomena, in insulators, superconductors, and metals, the theory of spin liquids, quantum antiferromagnetics, fractional phases of matter, and many other. His research describes the connection between physical properties of modern quantum materials and the nature of quantum entanglement in many body wave functions, and the application of these ideas to a priori unrelated phenomena such as black holes, and something he'll be telling us about today. Professor Sachdev has been received numerous awards. He's been elected to the National Academy, received the large Ansanger Prize from the APS and Dirac Medal from the International Center for Theoretical Physics, amongst many other awards. So we're delighted to have you virtually here, and we look forward to your colloquium.
Thank you very much, Professor Deutsch. It's a pleasure to be at least virtually in Albuquerque, and I hope in person someday. Thank you for that kind introduction. So as my title announces, I will be talking about quantum entanglement, and in particular, quantum entanglement as it appears in nature and complex materials in the lab, which then turn out to have some surprising connections to the nature of quantum entanglement across black hole horizons. Now, I'm not a black hole physicist, but I'll try to give you some sense of my understanding of the connection to black holes, and which has led to, especially in recent years, many advances in understanding the nature of quantum information in black holes. All right, so let me just begin by first defining what is quantum entanglement. Just in the small chance somebody needs a refresher. So quantum entanglement is basically the idea of quantum superposition, which is the very foundation of quantum mechanics, extended to more than one particle. So for one particle, you can have the electron go through the left slit or the right slit, but actually being a superposition state. Similarly, then if you have two electrons, say in a hydrogen molecules, the toy representation of the wave function of the two electrons is there's one state where the left electron has spin up and the right electron has spin down, and there's another state with the reversed spin assignment, and the actual state is the so-called spin singlet state, or the EPR pair, where the electrons are really in a superposition of both of these states. Now, what makes this kind of superposition much more mysterious intuitively is that the superposition can become highly non-local. And this is the famous EPR quote-unquote paradox. So if you could imagine separating the two electrons without disturbing their spin, then you would maintain the entanglement, and this entanglement would be highly non-local. So you wouldn't know whether this electron, which could be in my room, and the other electron, which could be in Albuquerque, which one is up and which one is down. In fact, it's not determined quantum mechanically. It's only when I look, if I look at my electron and find it to be down, then your electron necessarily up. Okay, and this is sometimes called the EPR paradox, which Einstein didn't find very palatable, but palatable or not, it's still the truth. We know this does happen. And it's not a paradox the only new concept that we have to get comfortable with is that the notion of a quantum state is not necessarily local. The quantum state is of these pair of electrons, neither here nor there. So it's not as if some information is traveling from here to there when I look at it. Okay, so that's a quick summary of what is quantum entanglement. And my objective in this talk is to talk about quantum entanglement, not of two particles, but really an infinite number of particles. Now, we are very far from any simple, complete classification of an understanding of the, the rich variety of entangled many particle states. We just scratched the surface, I imagine, of the kind of states that we can understand and see in the laboratory, and I'll tell you about some of those. So one particular model, which is called the SYK model, that's given us some insight to this vast space of quantum entanglement, is the following. So let me just describe it in its simplest terms. So imagine you have a bunch of orbitals, which I've just put at random positions. And each one of these orbitals can take one and only one electron. So I'm ignoring the spin of the electrons here. So I have these electrons then occupying these orbitals. These are the occupied orbitals. And this is one of the states in the Fock space of this many particle system. And now I'm going to give you a matrix element or a transition amplitude between any such state where you occupy any of these orbitals with some fixed number Q of electrons. And then you have a transition matrix element. And the key thing you want to do is to prohibit any electron to move on its own. And this really is a way of building in quantum entanglement. So suppose you had a physical situation where that was the case, where the electrons are prohibited from moving on their own, but could move in pairs. So for example, there's a certain matrix element for these two electrons to move to those two sites. And of course, it doesn't matter. You don't know which one goes where. So you can, of course, interchange which electron goes where. And there's some amplitude then for that process to happen. And then you can pick any pair of electrons, which are all in occupied states, and move them to any pair of empty states. So there's some amplitude for this process too, and so on. So to define the many-body Hamiltonian, I have to give you a number for each one of these two-body transfers. And every time this transfer occurs, the those electrons are entangled. And what makes it a many-body problem is that any given electron here can pair with any other. So you can pick any. You don't have to remember which pair you moved with the last time. You pick another electron as your partner, and then move it, and then move forward. Okay. So now I have to give for every one of these amplitudes. I have to give you a number. So, if I gave you a set of numbers for even, let's say 50 electrons or 50 sites, and asked you to tell me what the ground state looks like and what the excited state look like, that's an impossible problem. You can't put it on any classical computer. Maybe someday we'll have a quantum computer that can tell us something about it, or a quantum simulator. Okay, so however, there's one very interesting case where you can actually solve things in the limit of a very large number of sites for certain, properties, not everything. You don't know the precise state, but you know to high accuracy almost all of the observable properties. And that's the case where every amplitude which is allowed is an independent random number. Okay, so there's a whole set of random numbers, which lead to these kind of transitions in this many-body space. So some of you, may know about the random matrix model of nuclear structure, for example. Well, there is just a single matrix where every element is a random number, effectively acting on the possible states of a single particle. This is a much larger matrix because the number of states here is exponentially large. And I don't have an exponentially large number of random numbers. In fact, it's a very sparse matrix. I only have of order n to the fourth random numbers because I can pick the first 2 electrons roughly n squared ways and then move them to n squared positions. Okay, so that's what's called the SYK model. Although it did appear in nuclear physics a long time ago in something called the 2-body random ensemble. It was written down, but there wasn't anything understood about it at that time. I haven't seen any reference to it since this work in '81. There were some numerical studies, and that was it. Okay, so here's the model written out in operator notation. The electrons can go from site L and K to site I and J, and the amplitude for that process is this number UIJKL. And the basic idea is that these are independent random numbers. You can have any distribution you want. For convenience, we take them to have 0 mean, and some mean square value U. So in the end, there's just one number, one energy scale that characterizes this, that's Hamiltonian. There's a chemical potential which changes the number of electrons, which I'm going to call Q. Q will be the number of electrons per site. Okay, so now here's a well-defined problem. I have an ensemble of Hamiltonians drawn from this distribution, and n is going to become large. Now, one of the remarkable things about this ensemble is that it's self-averaging. That is, I just need one sample. I don't need more than one sample, even though I'm talking about an ensemble. In fact, if I just had one of these in my lab, it will behave essentially identically to high accuracy to the ensemble problem. So, and that's really the key to understanding why we can solve this problem. Since any individual element is the same as the ensemble, well, then might as well work with the ensemble. And then the ensemble is a lot easier to work with by various methods we know on how to treat random quantum systems that were developed in condensed matter really since this work. And that's presumably why the nuclear physicists in the old days didn't make much progress on this problem. I should say the problem that we solved is slightly different in '93, but had the same solution. And we were completely unaware that any such problems had been looked at in nuclear physics. Okay. All right, so now I won't, this being a colloquium, go into the details of how the solution proceeds. It's, as I said, it involves standard techniques in quantum many-body theory, including something called the replica method. But let me just highlight 2 remarkable properties of the solution. So what you end up getting is a gapless system. That is, you have a ground state, which is essentially unique. May have some trivial degeneracy of 1 or 2, depending on the geometry. And then there's a whole set of excited states. But unlike something like say the fractional quantum Hall state, there's no gap between the excited state and the ground state. The lowest lying ground state, excited state, is exponentially close to the ground state, exponentially close in n. And there's a whole continuum of very large number of states. Now, if I take electrons in a metal, they're also gapless, and they have a whole continuum of states. But we can describe the excited states rather simply by something called the quasi-particle concept. That is, we can build up, we can imagine we have some excitation here of my many-body system, of my metal, which I call a quasi-particle, which is like an electron, but with a screening cloud around it. And then I have another quasi-particle. And I can build up the many-particle excitation by just adding and composing these quasi-particles. And this idea of composing quasi-particles is really the very foundation of everything in the textbooks of condensed matter physics. It's really the foundation on which the entire theory of metals, insulators, superconductors, semiconductors is built on. The idea that excitations are quasi-particle-like and can be composed to create many-body states, many-body excitations. So this is now, of course, there are cases where this is not possible. And this is one of the simplest cases where that's the case, where you do not have quasi-particles. And it's really about the only case where even then you can solve for things exactly in some And that's really the interest in the system, that it's really the best known example. In fact, I think only the only example of a system that has no quasi-particles and yet is almost solvable by this trick of averaging over an ensemble of systems. So that's one of the key properties, and that turns out to be the key also to connection to black holes. And a close connection with, so then you can ask, what are the excitations? If there aren't lumps or particles that move around in some coherent way, what are the excitations? Well, you don't have a simple way of describing them, except there's some messy set of excitations. But what we do know is that they're highly chaotic. That even small changes in the wave function would immediately lead to exponentially large changes in the many-body states. And you characterize this by various techniques that have been developed to characterize many-body chaos in the last, I'd say, 5-10 years, including measurements of something called the out-of-time autocorrelation functions. And there are also believed to be certain bounds on how fast any system can, roughly speaking, thermally equilibrate if you perturb it. So you have this SYK model sitting there and you kick it, and then you ask, how long does it take before it just looks like a system at finite temperature? Well, it turns out there's a bound on how fast this can happen. This is something I conjectured, I don't know, 25, 30 years ago. And the bound is basically this, what's now called the Planckian time, Planck's constant divided by the absolute temperature. So, so the claim is that no system can equilibrate as fast as this. And this is the champion in equilibrating quickly or becoming chaotic. And it saturates the bound. It's h bar over t. And this is something you can prove, at least by computations on this Hamiltonian. Okay. Right. Okay. So for example, in a Fermi liquid or a metal, this time would be roughly 1 over temperature squared. Whereas here is 1 over temperature. So as temperature goes to 0, this is much, much shorter time. So in another way of saying this, this is just a joke. This is, the worst possible quantum computer because it decoheres as fast as possible. Okay, that's why I like it. But know the enemy, shall we say? All right. So now, but now let me tell you about one result that I want to focus on. There's the amazing connection between this. That's the model. I can, literally, it's just defined by these 3 lines. So even to somebody who knew no physics, and I just know a little bit of algebra of operators, then that's it. You can go to a desert island and go study it. I don't need to turn on anything else. That's it. But it turns out to have some remarkable properties, including connections to black hole, and a baby version of what string theory is called holography, and which I'll describe. But unlike string theory, you don't have to learn string theory and take 2 or 3 years of your life there. That's all you need to know. Okay. All right. So what's one of the basic statements of this? So say I'm looking to low temperatures and I'm computing the partition function of this Hamiltonian. Well, the claim is that you can write it this way. There's an overall prefactor which effectively gives you this number S0, which is the limit of the 0 temperature entropy. That's S0. And this S0 doesn't depend on any details of the model except the charge Q. And there were some relations that we derived a long time ago on how this entropy will change as you change the density of electrons. This is just for future reference that I'm mentioning this result. Okay, so that's the 0 temperature part of the partition function, just the low temperature entropy. And then there are temperature dependent corrections. And these temperature dependent corrections can be written as a Feynman path integral. And what is that? What is this Feynman path integral? Well, what it looks like is that it's first of all, the path integral is over this function f of tau, where tau is imaginary time. And we can really think of this f of tau as some kind of time reparameterization. So you have some coordinate time, and then you reparameterize the time. It's still monotonic, but you go faster, slower, faster, slower. This is the kind of thing you do in general relativity. You have space-time, and you have reparameterizations of space-time coordinates, and the whole structure of general relativity is invariant under reparameterizations. Well, here, there's no space, there's only time. So this is like a zero-dimensional system. And you have to do a path integral over all possible reparameterizations of time. And that's kind of what you would do in quantum gravity, where you do the path integral over all the metrics, for example. And what is the action for this? Well, the action, remarkably, is an action which can be interpreted as the action of two-dimensional gravity. So that's where the holography comes in. This is an action in 1 + 1 dimensions, whereas this quantum system you began with was in 0 + 1 dimensions. So you're going from if you go backwards, that's really this SYK model is a hologram of a two-dimensional gravity system. Now, 2D gravity, you may know, is kind of trivial because there is no graviton in 1 + 1 dimension. You can, just by choice of coordinates, you can make, you can get rid of everything. And the only quantity there is the integral of the curvature. But there's a slightly more complicated, it's not pure Einstein gravity, it's a slightly more complicated theory. It has the feature that there is still some real degrees of freedom left over, but they sit on the boundary. So basically, the only graviton that's in this theory is on the boundary, and this action is the boundary graviton. So in this case, you can explicitly show, in fact, this, and I won't write down the explicit expression here, there in the references, of this path integral of quantum gravity being exactly equivalent to at low temperatures to the partition function of the model I just showed you. All right, so that's the main claim, which I'll say more about, of course, that this model with many particle entanglement at low temperatures looks like a certain theory of quantum gravity in 1 + 1 dimensions. And this has, very powerful consequences. You can compute all kinds of things in gravity, which people have been doing in recent years by computing things here, and vice versa. And so it's been really a very useful two-way street. And I'll show you some of those results, hopefully before the end of my talk. All right, so now I want to just talk about a bit more black holes on their own. So let's just go back a bit in time and remind you a few basic things about black holes. So black holes are dense objects of matter, even classically. They are predictions of Einstein's theory of general relativity, prediction first made by Schwarzschild, that if you could compress a mass m to a radius smaller than this number r, called the Schwarzschild radius, then there would be a horizon at this Schwarzschild radius, and light would never be able to escape from inside to outside. In fact, the inside of the black hole will be causally disconnected from the outside. All right. However, quantum mechanically, there is a connection between the inside and outside. And one simple way to think about it is you do an EPR experiment. You take a pair of entangled electrons, and you throw one inside the black hole and the other outside. And quantum mechanically, they're still entangled. So it is indeed true if you are safely outside the black hole and you measure your part of the EPR pair, the other one will collapse inside. But you'd never know, of course. But there is still a correlation because whoever has the bit inside can't ever communicate to you, classically anyway. Okay, so there's quantum entanglement inside and the outside of the black hole. And Hawking, used very separate arguments to argue that this means that the black hole quantum mechanically has an entropy. It's not just a featureless black sphere sitting there. It's got all kinds of quantum degrees of freedom and has an entropy and also a temperature. And roughly you can think of this as if you have this qubit electron with you outside, as far as you're concerned, the other one's gone forever. So this is essentially a random qubit. So to you, looking at the black hole from outside, it appears there's some temperature there because you see these things coming out, which are just random. Okay, so right, so this is then summarizing Hab-Blackman temperature. So one of the remarkable things, and this is of course one of the keys to holography, is unlike any other physical system that we know of, the entropy of a black hole is not proportional to its volume, but it's to its surface area. And this intuitively you could understand from the fact that it's because of the entanglement across the horizon that the black hole has an entropy, and that horizon is the area of the surface area of the black hole. So because the entropy is only proportional to surface area, then you have the option, you have the possibility of holography of describing it as a quantum system without gravity, which is sitting somewhere on the surface or somewhere at the boundary of space-time. It's a for three-dimensional black holes that we are considering, it would be a two-dimensional surface somewhere. Would be equivalent, would have all the quantum information needed to describe a three-dimensional black hole. And now we have many such realizations of this remarkable idea. Okay, another very important thing I want to also note about black holes, which is where you will start seeing the connection to something like the SYK model. You could also ask, I've told you that the black hole is a system in thermal equilibrium, rather low temperature. You could ask, well, how long, so if you kick a black hole, how long does it take to thermalize? So here I have two black holes merging to form a perfectly perfect sphere. You can, and you can use Einstein's GR to figure out how long this ring down time is. For the first LIGO observation, it's a few milliseconds. So, not within the resolution of their observations. And this ring down time then is like thermal equilibration time. But from a quantum perspective, if I think of the black hole as being holographically represented by some qubits on the boundary of space-time, it's the quantum relaxation time of some ordinary quantum system without gravity. And what is that in this units of the temperature of the black hole? Well, it turns out to be this ring down time is basically nothing but Planck's constant divided by the Hawking temperature. So a black hole, like the SYK model, is also a champion in equilibrating as fast as possible. So this tells you immediately that if the hologram of the black hole, which is representing its quantum dynamics, cannot be a system that has any quasi-particles. It's got to be a system without quasi-particles. And that really is the reason for the connection between, ultimately, between black hole dynamics and SYK dynamics. Okay, so this is all really you need to know about black holes and the key facts that I'm going to use. All right, so now, in fact, you can make a rather explicit connection to the SYK model for a certain class of black holes in our four-dimensional space-time. So let's just take, the glorious theories of 19th century physics, well, early 20th century, Einstein's theory of general relativity, and Maxwell's theory of electromagnetism. And we're going to solve them in a situation where there's a black hole which has a net charge. It's hard to find such black holes out in the universe, but there are certainly allowed solutions where there's a net charge in the black hole, and then you want to look at it at temperatures or very low temperatures. Okay, smaller than the inverse horizon radius. So the solutions of Maxwell's electromagnetism and Einstein's relativity with a net charge, it's called the Reisner-Nordstrom solution of these equations. And it has a rather remarkable property that as you zoom in, so the space-time is curved or outside the black hole, but as you zoom in to the horizon, what you find is that the space-time factorizes. that is the radial direction metric, which is zeta, and the angular direction just become totally separate from each other. And so at low energies, or if you're looking at very low temperatures, all of the interesting dynamics is purely in the radial direction. So you end up getting very naturally, at least in the low energy limit, a theory of gravity in 2 dimensions. So this is, this is wonderful because, when I first said the SYK model was dual to a theory of gravity in 2D, you say, well, who cares? We don't live in 2D. Well, it turns out even in 4D, there are situations where 2D gravity is a relevant low energy limit. And it turns out the 2D gravity you would get by quantizing Einstein general relativity and Maxwell electromagnetism in this low energy limit is the same theory you get from the SYK model. So in that sense, the SYK model is a hologram of this one-dimensional theory of gravity, one space dimension, which is the radial direction of a charged black hole. Okay, so that's that's the claim anyway. So just to show you a few equations, this is what you have to do. Of course, I won't show you any more details. This is the Einstein-Maxwell action. You have a metric G. From the metric G, you can compute the Ricci scalar. There's a cosmological constant, which you can make as small as you want, but it helps to make it a small negative value. Kappa squared is related to the Newton's constant, and that's the Maxwell electromagnetism. And you solve these equations, the Euler-Lagrange equations of this action, with spherical symmetry, with some boundary conditions, that electric field go to infinity is some net charge over 4 pi r squared. The metric also, as you go out, if this curvature is a cosmological constant negative, is not Minkowski but ADS, but that's not so important for, at least for our discussion today. Okay, and then having solved the Euler-Lagrange equations, I have to then integrate over all gauge fields and all metrics to get the partition function of quantum gravity. Okay, so this is the very naive definition of quantum gravity, and it's surely completely nonsensical because it's full of infinities. That's why string theory was invented, for people to be able to evaluate such path integrals and make sense of them, because there's all kinds of infinities, and this path integral doesn't make sense in general. However, if you're satisfied by just focusing on the very low temperature properties of a charged black hole, which I will be for this discussion, then actually you can evaluate this integral and work out the full gravity theory. And curiously, these steps could have been taken, 50 years ago, but they weren't, because nobody ever really believed that there was any sensible theory of quantum gravity in 2 dimensions until the example of the SYK model showed that indeed there was. Okay, but you didn't need the SYK model to get where we are going, but it was only after it was known that people figured out the connection.
Sachdev, we have a question, so maybe.
Yes, please.
Go ahead, Tamid.
So just to be clear, does the charge of the black hole here map to the chemical potential in the SYK model?
Yes. I mean, okay, it's not completely literal. There is I will show the connection in a minute, but that's correct. Yeah, there's a charge on the SYK model also, the Q. I mean, I'm using the same symbol Q. If you remember, there was a Q here. So this Q, which is just plays a role very similar to the Q over here. Okay, I should have made that script Q for that Q. Okay, any other questions? All right, so first, let's just do the solution of the Euler-Lagrange equations, and here explicitly I'm displaying this factorization property. So this is the part of the metric that's called ADS2. This comes from the solution of the 4-dimensional equations. And zeta is the radial direction, t is time, and this is the ADS2 metric. And the important point is that zeta and time don't ever appear on this side, where this is just the metric of the surface of the sphere, a two-dimensional sphere. And there's some electric field coming out from the black hole, from the horizon here. Zeta goes to infinity at the horizon in these coordinates at 0 temperature. And the electric field is, of course, just given by Gauss's law. So there's some net charge inside. And so there's a, if you wish, you can neutralize the charge out at infinity with the electric field going out there. All right, so now we just look on the quantum fluctuations on this part of the metric. And amazingly, it turns out you can just do that calculation. It's a very clever calculation. I think it was done by Maldacena and Stanford and Yang, and also Kitaev. But in principle, it's not anything that fancy. It's just a question of finding the right variables and fixing the gauges and so on, and just doing that path integral. Okay, but before I get to that, I forgot to mention this. So this, you can relate it to the question that was just asked. You can, by Hawking's formula, you can compute the entropy of this black hole. And you can also compute how it depends on the charge Q. And it turns out that this relation that I mentioned earlier between the derivative of the entropy with respect to charge. So if you throw more charge into the black hole, the entropy will increase. And it turns out that from the Einstein equation, you get this relation that the rate of increase of entropy with charge is the electric field on the boundary of the system. And this same relationship is also obeyed by the SYK model. And this was actually one of the first hints that there's a connection between these two cases. Okay, so now I was going to talk about quantum fluctuations of this 2D gravity theory here. It turns out that the only interesting quantum fluctuations are in the boundary. But what is this the boundary of? Well, it's the boundary between this regime where there's a factorization, where space-time factorizes into a two-dimensional space-time and a two-dimensional space, to a regime where it doesn't. So out here, there is no factorization. So you go from a four-dimensional space-time to a two-dimensional space-time, and there's a boundary there. And it turns out that all the low-energy quantum fluctuations of this black hole are just represented by this boundary. So now you can get a theory for this boundary. And that theory of the boundary gives you exactly the same expression I showed you earlier. I'm not writing out this particular, what the explicit expression is. It's known, of course, there's something called the Schwarzschild for the experts. Maybe I should have written it out. Anyway, so now the remarkable thing is you can derive this now in two different ways. One way is by start with the SYK model and write down its Feynman path integral and just manipulate it in a clever way. And the other, you start from this theory and just, again, manipulate it in clever ways, and you end up with the same answer. So there's a rather explicit connection where you can prove that for a general charged black hole, at least for the low energy degrees of freedom, that there's a hologram. The hologram of the black hole, which is now effectively living in two space-time dimensions, is this zero-dimensional SYK model. Okay, and these are some of the references of the various people who have contributed to these connections. All right, so what I've shown you here, somewhat more explicitly than the other trick, that you can go from charged black holes, and at low temperatures, there are a certain theory of quantum gravity in 1+1 dimension. And amazingly, it's the same theory that you get as the low energy limit of this very simple model of multi-particle quantum entanglement with random amplitudes for two-particle entanglement. Okay. And, it might seem rather mysterious that this kind of miracle happens, but really the miracle happens is because there's essentially only one class of systems in zero space dimensions which have these properties, that have complex multi-particle entanglement without quasi-particle excitations, and that we think is also the key to the quantum physics of black holes. And this many-body chaos and thermal equilibration and dephasing and decoherence in the shortest possible time. Okay. All right. So how am I doing on time? So I have about 10 minutes left. Is that correct? So let me now try to bring in the final actor. This is all this. I presented this because it's really it's easy in this subject to have lots of speculations and vague ideas, but I want to impress upon you that there's a very specific mathematical result here, which is quite remarkable, which really I've outlined, what the statement of that is. Okay, but now let's get to the world I normally live in, which are things like high temperature superconductors. So here's an example of the system I'd be interested in, yttrium barium copper oxide. But for our purposes, it's nothing but a square lattice of copper ions. And there's just one orbital on each copper site. So you can think of this as, in a certain limit, as electrons that are moving on the square lattice. And if you had one electron for each site, what they will do, because of the nature of the coupling between them, is first of all freeze their charge and become an insulator, and they would have form this checkerboard arrangement of up and down spin called an antiferromagnet. But it turns out that you can change the density of electrons, so you remove a few electrons, and then you get what we call a doped antiferromagnet with their empty sites of density P. And now these can move around, and the amplitude for any one of these holes to move is called P is T. So these are the process, so that the electrons are moving or the hole are moving either way. And then you can also have a spin exchange J, where any pair of spins and holes can move, and there's T's and J's and so on. So this is the famous TJ model at finite density. And we'd love to solve this. Unfortunately, after 3 decades of effort, we know very little, at least at low temperatures, we know precious little about it. Of course, there's no shortage of theories. However, the reason it's so hard to confirm or check those theories is that there's a sign problem. If you go to below a temperature, I would say of order J even, below. So in the real world terms, that corresponds to a temperature of about 400 to 300 Kelvin. Basically, you can't go below the temperature in a numerical study. So perhaps a quantum simulator will tell us more. But for now, let me tell you about some ideas that we've been playing with. Okay. So what you can always do, this is the world's best quantum simulator. You can actually do an experiment. You can measure a few things. So this is what you see as a function of hole doping and temperature. I've shown you the antiferromagnetic insulator, and you get what's called a high temperature superconductor with critical temperatures of order 100 Kelvin. We'd love to understand, so goal number 1 for a quantum simulator was to compute TC of the TJ model. Maybe someday they'll tell us what it is. Okay, so however, my focus in the remaining 10 minutes is not on the superconductivity, but the region above the superconductor, which is a metal, but rather bizarre types of metal. So out here in the blue is in fact a familiar metal. It's what we call a Fermi liquid, very similar to that you might find in a metal like copper or gold or silver. Down here we have a pseudo-gap metal, whose nature I'll say a little bit about. And in between we have the strange metal, for want of a better name, where in fact it's the strange metal that ultimately has some connections to the previous topics, to Planckian relaxation and many-body chaos and absence of quasi-particles. Okay, and it was trying to think about the strange metal that led us in '93 to propose that type of model, just a toy model. Okay, so let me just show you a few experiments about these 3 metals, about 3 metals. So one way, let's start on the extreme right over here, where we have a Fermi liquid. Now, if you remember your solid state physics, or even if you don't, let me remind you, the way you treat metals, you go to momentum space, and you think of each electron as being in a plane wave state, and you just fill up the lowest energy plane wave states. And that's a pretty good theory of a Fermi liquid. So how would I do that here? Well, it's more convenient to think in terms of holes and take this momentum space view, but holes in what? Well, for the field hole picture to work, you have to start with a filled band. And a filled band is not 1 electron per site, but 2 electrons per site. So if you started with 2 electrons per site and took a momentum space view, this configuration with hole density P is really in momentum space hole density 1 plus P, because you have one hole on every side as it is, and then you took a few more. So this, in the Fermi liquid terms, is a system with 1 plus P holes. And now there's another deep theorem of Fermi liquid theory, which tells you that the Fermi surface, the surface in momentum space, which bounds the occupied states from the empty states, has the same volume as that of free electrons. So all you have to do is measure the Fermi surface, which is done here in a photo emission experiment, and see how much area is enclosed by the Fermi surface. And bingo, you find it's exactly what you expect. When P is large, you get the value of 1 plus P to some high accuracy. So all is good on the right, where you have a Fermi liquid. However, when P becomes small, in the pseudo gap regime, we have no idea what this photo emission is saying, and there's still a lot of debate on what's going on here. And we have some guesses, but it's clearly not just free electrons. So one recent experiment that's been telling us something about one class of materials that in the pseudo gap regime, this particular experiment tells us that in fact it's some kind of spin glass. So this is the low doping pseudo gap where there is no Fermi liquid. Fermi liquid is out here, and here it looks like there's glassy behavior, at least in some applied magnetic fields. Okay. And in between, there's a strange, so I've told you a little bit about this, In between is a strange metal, which is what I really care about. And I show you here a very beautiful recent measurement of Planckian scattering. This basic wonderful time of h bar over kt again rears its head. And in this case, you do something called angle-dependent magnetoresistance, and you look at the relaxation time of the electrons. I won't go into any more details. And you find that there's an isotropic contribution, which doesn't depend on angle, which is to within a factor of, a few, about, I think, 50% or so, precisely this Planckian time, meaning that it's independent of any other energy scale in the problem other than temperature itself. So this is a hint that something Planckian and maximally chaotic is going on here, similar to the other systems we talked about. Okay, so I have just 2 minutes at the most, I think. So let me just tell you about our recent work to try to understand this set of experiments, and I'll be a little quick. So we'd love to solve the TJ model. And I've told you what experiments are telling us about the TJ model, and we can't solve it really. However, we had the idea, inspired by the similarity to the SYK physics, we said, okay, let's look at, this is work with collaborators at Harvard and at Flatiron Institute. Let's look at the following model. In the spirit of the SYK model, we'll take the TJ model with electron hopping and spin exchange, but make these numbers random numbers, okay? So here are, instead of putting things on a square lattice, I just put them on a cluster. Just simplify the problem as much as you can. So each site can have 3 states. It can be empty. It can have a spin up electron or a spin down electron. In the SYK model I told you about earlier, there was no spin. Okay, so that's the 3 states per site, not 2. And the interactions now are much more realistic. You can have single electrons move around. So that electron can move with amplitude t, but now we have them move randomly between any pair of sites. So that's the part we keep from the SYK model. There's random Tij between any pair of sites and random j between any pair of sites. So there's the model. And amazingly, now this random model, we can't solve it exactly the way you can solve the SYK model, but we've been making a lot of progress. And one of the things you can do is just put it on a classical computer and diagonalize it. And that actually works better than for the square lattice because you can take many samples because you believe the system is self-averaging, you can just average. And that gives you the large N limit in a much smoother way. That it's really just as simple as that. And so what are some of the things we see? Well, we see things very closely related to what you observe. You see that above a certain P, there's a large Fermi surface. I won't go into the details of how you see it. And there's an analog of a large Fermi surface above some PC, but not below. And below PC, you see this peak here, and that peak in the spin susceptibility, and that's the spin glass order, that the spins freeze and have a definite orientation. So you see both the pseudo gap-like phase and the Fermi liquid-like phase. And then finally, what you see in between, well, you see the spectrum here. And the spectrum has a frequency dependence, which is actually exactly what you'd expect from the SYK model. So although this is not the SYK model, this is essentially the TJ model, but with random couplings. So among other things, you can, in the SYK model, you can compute this quantity. And among things, you find this Planckian dissipation with time h bar over kt. And this frequency dependence, this linear frequency dependence here, this thing, is constant plus a linear. So I showed you this constant becomes this Planckian tanh. And then this linear part, which is this term here at finite temperature, that is the contribution of the boundary graviton in this model. So if you work through holographically and then work backwards, what the contribution is for this particular physical quantity in this TJ model, this is linear frequency dependence of the spin susceptibility at the critical point, which you see in our numerics. Okay, so to summarize this random TJ model, simple as it is, captures some essential features of the physics, including the appearance of a large Fermi surface only at high doping and Planckian type criticality near the critical point. And we also have various papers where we understand the behavior of this and the connection to SYK, a bit better than I've had time to talk about. All right, so I'll conclude. This is what I've talked about here. And these are all this SYK model, the copper-based superconductors and charged black holes are systems that are connected. These are connected by 2D quantum gravity. This has SYK criticality near PC. And these are all systems without quasi-particle excitation, complex many-particle entanglement, and very rapid decoherence in the time h bar over kt. Thank you.
Very good. I ask everyone to unmute and great. All right. Well, lots of fascinating concepts intertwined here. We have time for questions. Just unmute and ask a question if you have one.
I have a very simple question. I heard you say something like a sign problem occurring in one of the
Yes,
theories you discussed. Did you mean SIGN?
correct.
I see.
So if you take this TJ model here, so these are fermions. The arrows are fermions. They're moving around. So what can happen is that this fermion can hop from here to there. So and then these two spins can exchange. And so the holes moving around, the spins exchange, and you want to sum over all of these. You imagine doing a path integral over these. So each path integral, each time evolution has a certain weight, but it's not a positive number. It can have either sign. And in fact, the average sign is 0 as the system becomes bigger and bigger. So this means that if you try to sample this in a Monte Carlo simulation on the computer, on a classical computer, you're bound to fail over any reasonable system size or below a certain temperature.
Did you describe this in some particular paper, this sign problem?
This is not me. This is not my work at all. There are, I mean, they have probably books written on it by people who do quantum Monte Carlo, but it's not something that I'm not a numerical person at all. I mean, is there a rigorous proof that there's a sign problem here? I don't think there is. But so what in practice, people try to do Monte Carlo and they keep trying to come up with better and better and better algorithms. So far, no one's ever succeeded that didn't have a sign problem. It's more of a trial and error thing, where you put this on a computer and see what happens. And you say, oh, I have a new algorithm that's going to cure the sign problem. Well, let's see. And so far, any such idea has failed.
Well, a graduate student named David Amdahl and I have worked on this and have developed a new method for dealing with the sign problem.
Okay.
But we would talk
For which problem?
Scalar fields in 4 dimensions. We weren't discussing fermions, but the method that that we developed may work. I don't know in the theory you are talking about.
Right. So, I mean, there are many systems, there are many quantum systems in which people have succeeded in overcoming the sign problem. They're typically ones that either have only bosons, or if you have fermions, they have a certain particle hole symmetry. So for example, QCD, if you were just discussing, if you're doing QCD, which has fermions, but it's, just for a few quarks, there's no sign problem. However, if you're doing finite density QCD, if you're doing nuclear matter or a neutron star, then there's a severe sign problem. So the moment you get a finite density of fermions without particle hole symmetry, then as far as I know, no one's ever solved that problem under any condition. So you need a finite density of fermions, not equal. If you have fermions, where there's a antiparticle for every particle, then there's no sign problem. Then you can come up with algorithms and get rid of it. And for scalar fields, at least for equilibrium properties, there's no sign problem, but for non-equilibrium properties, there almost always is.
In scalar field theory, it depends on the Lagrangian. You can have Lagrangians for which the Hamiltonian is very hard to find because the action isn't quadratic in the time derivatives.
Right.
The scalar fields. Those are the things that we were discussing. Anyway, I'll let you.
Okay. Yeah. Right. So, but that's the kind of thing I can believe that you come up with a very clever method for conquering that problem. But I believe the finite density fermion sign problem is much more severe.
Different. Yeah.
Very good. Other questions? I have one question. So in the original, the SKY model that you set up originally, there are certain statistics that you assume for your random matrix that I get there, perhaps Gaussian ensemble. Is that important?
Actually, no, it's not important. What is important is that these U, I, J, K, L are independent random numbers. That's all.
But they can have any statistics you like, and you get the same essential properties of no quasi-particles, etc.
That's right. You get. I mean, there's a kind of a central limit theorem. So this thing just always, then very, very rapidly, more rapidly than almost any other system, approach any site starts looking like any other site. Because really, roughly speaking, every site is connected to every other. So, even if you take one sample, this particular site is seeing all the other sites And so it basically samples the whole distribution, pretty much. And the only things that matter in the large N limit is that the distribution is the second moment, somewhat similar to the central limit theorem of statistics also.
Very good. Other questions? Maybe I have one more question. How close do you think we are to understanding high temperature superconductivity? Are we getting there?
Yeah, I would say so. I mean, if you want to say how close, it depends what you mean by understand. Do we have the basic physical ingredients and the basic understanding of the nature of the phases and the nature of the superconductivity? I think we're already there. But if you're asking, if I give you a TJ model or a Hubbard model and you tell me what the TC is, then we're very far from that. You could say, well, what about, you would say the problem is sort of like QCD. It's a strongly coupled theory, but now we can go to a powerful computer and compute the proton mass. We can. So in that sense, it's understood. We are nowhere near being able to compute TC for this problem, even if I tell you the full Hamiltonian. Yeah.
All right. Last chance for questions.
So maybe I'll ask a quick question. So in your, in that expansion that you showed where you were, calculating the constant and the linear part and comparing to experiment, and you said that alpha.
I wasn't comparing to experiment.
Or at least for the model.
I was comparing this is towards the end of my talk, right?
Yes.
Yeah, so here's the random model. And what we do is we do numerical study of this random model, and we're comparing that numerical study to theory. Okay. There's no experiment here.
Oh, okay.
Okay, go on.
So my question is, this constant alpha, does that signify anything about sort of the underlying physics? Like, could different models have a different constant alpha that actually means something?
I'm sorry, which alpha are you referring to?
See, because I think I was thinking more about, where you were showed the experiment.
Oh, you were actually talking about the experiment. Yeah, that's a total mystery.
Okay, yeah.
Yeah, that's a complete mystery. Why the alpha is so close to 1 and pretty much the same in several materials. Yeah, that's a complete mystery. So, yeah, so the point is, there's this mystery where you seem to get this h power over kt appearing in the real system. I don't really understand it. So we said, okay, let's just take this toy system and see if you get anything like it. And lo and behold, you do. So it's for this toy model with the Tij and Jij random, I can get basically the whole set of phenomena, which are exactly what you see in the experiment. What I can tell you is, why should this toy model be so successful? We don't know. Yeah.
But then does
this
the toy model
that we can solve?
But does the toy model fit like the 1.4 or let's say whatever 1.5?
Well, that would be. We haven't looked at. I mean, you'd have to figure out how to define it even, because that's something you have to do with the Fermi surface relaxation property. Yeah, I mean, I think you could define some analog of that. Yeah, we haven't looked at that. Yeah, we haven't looked at that. That'd be quite hard to actually do, even for the toy model. The sign problem, because it's a real-time finite temperature property. That's hard, but I think it's in the realm of possibility that we could look at that. It's a good suggestion. Yeah. Yeah.
Very good. All right. Well, let's thank Professor Sachdev again.
Thank you. Thank you very much.
Thank you so much. Really fascinating. We appreciate it. And I'll just hang out for a little bit. Very
all right.
Have
very
a good
nice to meet you all.
Thank you so much. We appreciate it.
Same to you. All right. Thank you.
Bye-bye.
Bye.